Hello, everyone, and welcome to today's webinar, Textiles 101, presented by Alyssa Decker, Director of Global Textile Development and Procurement for Moss Incorporated. My name is Annie Castle, and I am the Events and Registration Coordinator here at IFEI, and I will be moderating today's session. You will have the opportunity to submit questions or comments to Alyssa by typing them in to the questions box of the control panel. You may send your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. With this, I would now like to introduce today's speaker, Alyssa.
Hi, thanks so much. So today we're going to go through Textiles 101. Sorry that we are a couple minutes delayed here. This is the first time I'm running this webinar live, and we're learning that the file size combined with some other working from home challenges is causing a bit of a delay. So please bear with me. I think we are advancing to the next slide here. Okay, and these are, today we're going to cover fabric fundamentals, starting with fiber. Then we'll talk about yarn, fabric construction, dyeing, and lastly, finishing. So the first two, or there's really two main fiber types. One is natural, and the second is manufactured. For natural fibers, they could be from either plants or animals. So we're going to start with an example of a plant fiber or a cellulosic fiber, and that is cotton. Cotton is grown in a staple fiber. So a staple fiber is basically a short or defined fiber length. So this cotton fiber grows in about 1/8 inch up to 2.5 inches. Cotton is cream colored. It needs to be bleached to have a true white color. Cotton has low elasticity and resilience. It's easy to wrinkle. It has a high moisture gain of 7 to 8%, and strength of cotton increases when it's wet, and it's also susceptible to mildew. Some examples of other natural cellulosic fibers include flax, bamboo, hemp, ramie, and jute. So any plant-based fiber that's made into textile is considered cellulosic. On the other hand, we have protein fibers. Protein fibers come from animals. So an example of a protein fiber would be wool. Wool is also a staple fiber. Its length is 3 to 5 inches typically. And fibers vary in color between whatever color your sheep is. So if you have a white sheep or a brown sheep, that's going to be, of course, the color of your fiber. Wool has high elasticity and a natural crimp that increases its bulk and springiness. Wool has a moisture gain of 15% and low water repellency. Kind of this high moisture gain, but low absorbency and high water repellency comes from the scales. So the scales of wool help to shed the water off, but once water does seep in, it can have a very high moisture regain. Wool is a relatively weak fiber, and its strength decreases when it's wet. Another feature of the scales of wool is basically they allow the fibers to get entangled and then move in one direction only. And this is what helps wool to shrink. So if you think of washing a wool sweater and it coming out smaller and smaller and smaller each time you wash it, It's because these scales click together almost like a zip tie. Also, wool is susceptible to damage from moths. Some other examples of natural protein fibers coming from animals in staple length include cashmere, mohair, alpaca, angora, camel. We also can get protein fibers from silk. Instead of being a staple fiber, silk is a filament fiber. So the filaments of silk are come in 300 to 1,000 meter length, and each cocoon of silk is about the size of a peanut. The fiber color is white to cream, off-white to cream. Silk has medium resiliency, a moisture regain of 11%. And what holds the silk fiber together in that cocoon is a gum called sericin. Most silk is degummed, and that means that the sericin is removed. If the sericin is not removed, it's called raw silk. After the silk is degummed, it has a high luster, and silk is also susceptible to damage by sunlight. Moving from natural fibers to manufactured fibers. So early analysis of natural fibers by chemists revealed that the fibrous qualities depended on long chain polymer structures. So scientists took this information that they learned from the natural fibers and believed that if they could synthesize those long polymer chains, that they could eventually invent a totally synthetic fiber that didn't have any natural substance, basically. So in the 1930s, as early as 1930, some testing began on creating these long polymer chains structured similar to natural fibers. And in 1938, research resulted in the invention of nylon, which was the first truly synthetic fiber, and that was developed by DuPont. So here are some characteristics of nylon. Nylon is produced in a filament form. It has a circular cross section. It's naturally lustrous but can be delustered. It has excellent abrasion resistance, 4 to 5 times more abrasion resistant than wool. Nylon has a relatively low moisture regain of 4%. It dries very quickly. And nylon also has very high strength, which makes it possible to produce very fine yarns. Nylon has good dimensional stability. It does not shrink or stretch out of shape. And it has good resistance to microorganisms, insects, sunlight, and aging. Polyester is another example of a manufactured fiber. We're going to talk about 4 manufactured fibers. So polyester can be produced in staple filament or fiber fill form. Polyester can be made in a variety of cross sections, including round, trilobal, and hollow. It's naturally lustrous like nylon, but can also, like nylon, be delustered. Polyester has excellent resilience and good dimensional stability when it's heat set. It's relatively strong, but the strength depends on how the fiber is made, the size of it and the cross section. Polyester has a very low moisture regain. It's less than 1%, and it wicks moisture rather than absorbing it. And polyester is also resistant to microorganisms, insects, sunlight, and aging. Polypropylene is another example of a manufactured fiber. Polypropylene can be made in a variety of cross sections. It has very good resilience and good dimensional stability. It's almost completely non-absorbent. It has good wicking and it's relatively strong. Polypropylene cannot be subjected to high heat though. This is a fiber type that you wouldn't ever want to put in your dryer, for example. It has a very low melt temperature, so it can't be subjected to temperatures above 250 degrees Fahrenheit. Like nylon and like polyester, polypropylene is resistant to microorganisms, insects, and aging, but it will degrade in sunlight. The last manufactured fiber that we'll talk about today is spandex. Spandex is an elastomeric fiber, and the definition of an elastomeric fiber is a polymer which at room temperature can be stretched repeatedly to at least twice its original length, and after removal of the tensile load will immediately and forcibly return to approximately its original length. So basically this is saying an elastomeric fiber is defined as something that you can stretch over and over again, and it will recover back to its original length. So spandex has been manufactured in the US since 1959 in a variety of cross sections. It can be made in very fine deniers. The most important property of spandex is its ability to stretch and recover. Spandex is susceptible to damage from chlorine, as well as exposure to light, which can cause yellowing and degrading. Spandex is always used in conjunction with other fibers. So you'll see it a lot of times as a polyester spandex or cotton spandex, nylon spandex. Great. Okay, and here are some other examples of manufactured fibers: acrylic, acetate, rayon, modal, fiberglass, and carbon. We are going to move from fiber types now into some manufacturing. So the first step in manufacturing a textile, usually, for wovens and knitted fabrics, is making yarn. So we're going to talk about making staple fibers, or the short length fibers, into yarns. So at first, staple fibers were twisted together by hand. It wasn't until 500 to 1000 AD that the spinning wheel was invented. So if you think about that for a minute, actually making yarns is relatively new here. As we get into the Industrial Revolution in the 1700s, that's really when textile manufacturing changed and went from something made by hand to much larger production scale. So the first mechanized spinning began in 1741 with an invention that used a roller drafting principle. Later on, they were able to take that same machine and power it with water. So that was the water frame. And around that same time period, a second spinning machine was invented called the spinning jenny. What was really exciting about this machine is that it allowed someone to make it allowed production of 8 yarns at one time, and then was later modified to produce 16 yarns at one time, and eventually as many as 100. So that was a very, very significant change in yarn manufacturing. These are the basic steps for making a spun yarn. So the first step is opening. So this is, you get a bale of fiber and you open it. Basically just it's bound together in some way, and you open it, and after it's opened, the next step is cleaning. Cleaning would really apply more to a natural fiber like a cotton or wool would need cleans. After the fibers are cleaned, the next step is carding. Carding is a process that's like taking 2 brushes, moving in the opposite direction of each other. Carding is what helps the fibers align into one single direction. After carding takes place, the next step is drying. So it's taking those fibers that are all aligned in one direction and starting to draw them down into something that looks closer to a yarn. Roving is again just another step where that carded fiber that's been drawn now gets one step closer to being a yarn with the roving. And then the next step is spinning. So that's actually imparting the twist to the yarn. For filament yarns, the manufacturing steps are a lot different. So filament yarns are made from long, continuous strands. Most filament yarns have multiple fibers. If they don't, it's called a monofilament. So if you think of a fishing line, that is a monofilament yarn. Filament yarns are produced using spinnerets. Each spinneret has the exact number of holes, usually about 20 to 120, needed to produce a designated number of filaments for one yarn. So the spinnerets will also determine the cross-sectional shape of each fiber, whether that be trilobal, round, delta, or hollow, or another shape. Also, yarns made from straight filament fibers are smooth and slippery to the touch. They lack warmth, bulk, and comfort of spun yarns. And multi-filament yarns are made more cohesive or bulky by twisting or texturing them. So if you don't want that smooth, slippery touch, then texturing the yarn would be a step that would help make the yarn more similar to a natural fiber. These are the basic steps for making filament yarn. So the first step is extrusion. So the fiber pellets are heated up and then extruded. And I'm showing the shower head here to try to represent a spinneret. So basically how the fibers come out of the spinneret and have the same number of filaments as the finished yarn would have. Then the next step is drying and then twisting or texturing. Also at the bottom of the screen here, you can see the different cross-sectional shapes that I've been describing. So you can see how a trilobal yarn shape would look versus a round, delta, or hollow. This slide here is talking about yarn sizes and how they're measured. So staple yarns use an indirect method of measuring the yarn size. So indirect method measures rely on the measurements of fixed weight of yarn. The higher numbers indicate finer yarns, and examples of staple yarn sizes are 20 singles or 18 singles or a 10 double or like a twisted yarn, for example. So the first number is telling you your yarn size, and then the second number is telling you how many plies of the yarn that you have. So in the indirect method of yarn sizes, I think what's helpful is I think about buying shrimp. So the bigger your shrimp is, or the shrimp are, the lower the number counts. And that's kind of how it works with the indirect method for yarn staple sizes. So the bigger your yarn is, the smaller the number will be. For filament yarns, they use a direct method. So direct measurements rely on the measurement of fixed weight of the yarn. So a specific length is measured and weighed to give you the yarn size. Lower numbers indicate finer yarns, and examples of filament yarn sizes would be like a 70-34 or a 70-72. maybe a 150/48. So as these numbers get bigger, it means your yarn size is getting bigger. The first number tells you what size or denier the yarn is, and then the second number tells you how many filaments you have, or how many individual extruded filaments there are in total making up the one yarn. So you can have a yarn that, two yarns that are 70 denier, but they have different filaments, a different filament count. So it would mean the yarn is the same exact size, but one has more filaments. The 70-72 would actually be considered a micro denier. Anytime you have one denier per filament, that is a micro denier yarn. Here are some directional fabric terms. So everyone hopefully is familiar with these terms, but weft describes a fabric's width direction. It can also refer to the set of yarns in the horizontal direction. And warp describes a fabric's length direction, or could also refer to the vertical set of yarns in a fabric. For fabric construction, there are three main types: woven, knitted, or non-woven. So a woven fabric is created by yarns that intersect at 90-degree angles. The warp yarns that run in the vertical direction will have a insertion of a weft yarn into the warp yarn. So that weft yarn is inserted into the fabric with a shuttle, or it could be air or water, or some type of method that is moving that yarn across the fabric. Woven fabrics have typically low or no stretch. They have very good dimensional stability. They tend to fray at the edges. So that's how you can easily identify a a woven fabric. Everyday examples would be denim or sheets or a dress shirt. So those are all woven fabrics typically. And in industrial textile examples, maybe like an awning fabric or a seat belt. Woven fabrics are, they have ends and picks. So an end is the name for a single warp yarn, and a pick is the name for a single weft yarn. So when you're identifying quality of the fabric, sometimes you'll talk about the ends per inch, EPI, or the picks per inch, PPI is another just way that we talk about fabrics sometimes. Knitted fabrics are created by looped yarn intersections, and they use needles. Here I'm showing an example in the middle photo. You can see an example of a latch needle that is used to create stitches. Knitted fabrics have stretch in one or both directions. They're very flexible with good strength. Knitted fabrics can sometimes curl if they're unbalanced. And everyday examples would be sweaters, socks, and t-shirts. Those are all examples of knitted fabrics that we use every day. And then industrial textile examples would be maybe geotextiles or netting. So in woven fabrics, we have ends and picks. In knitted fabrics, we have wales and courses. So wale is the term for a single column of loop stitches, and courses is how we would describe a single row of loop stitches. So we would have WPI, or wales per inch, or CPI, which would describe the courses per inch. The last fabric type is non-woven fabrics, and non-woven fabrics are created by randomly placed fibers that are bonded together. Fibers can be bonded together by a variety of different methods. This could be a mechanical bonding, an adhesive or chemical bonding, or a thermal bonding. woven fabrics typically have low strength and they're low cost to produce. Everyday examples of non-woven fabrics would include dryer sheets, felt, or maybe a reusable grocery bag, those polypropylene bags that have the embossed pattern. Industrial textile examples would include filtration, carpet pad, and disposables. So now that we've covered fabric construction types, we're going to move into dyeing. So here are 3 methods of dyeing fabric. So the first method is beam dye. In beam dye, your unfinished fabric or gray fabric is rolled onto a metal cylinder or core that is perforated. Then this fabric on the perforated core goes into a machine where pressure is applied and the dye and all the chemistry for dyeing the fabric is put into this machine and filtered through the fabric through the perforated metal core and the pressure to impart color. So this is called beam dyeing. The fabric stays on the beam and it is dyed throughout. The second method of dyeing fabric here is jet dyeing. So jet dyeing takes gray fabric. It's also dyed under pressure, but the method is different. The fabric is circulated throughout the machine. It's kind of more like a washing machine process for jet dyeing. And during this jet dye process, the fabric is agitated. So this adds bulk and usually some softness to the final fabric. The third method on here is pad dye. So with pad dyeing, fabric is dipped into a solution and then it goes through a squeegee that will remove the excess chemistry. And pad dyeing is typically done in a continuous process. So this may be during the finishing process where you'd see pad dyeing. Pad dyeing is also commonly used for white fabrics that only receive optical brightener, as an example. Here are some methods of dyeing fiber and yarn. So the first method is fiber dye. So this means you have your loose fiber. This is typically staple fiber, and taking that fiber and dyeing the fiber before it's made into yarn. When you dye just the fiber, you can take those different colored fibers and combine them to make, for example, heathered yarns or a multicolor yarn. Another method of dyeing would be yarn dye. So this is taking a finished yarn, a white yarn, maybe a cotton yarn in this example here, and you dye the yarn after it's already finished. So with yarn dyeing, sometimes the color does not go all the way to the bottom, all the way to the inside core of the yarn. And an example of a type of fabric that uses yarn dyed yarn very frequently is denim. So as you wear your denim, you will see that the color gets lighter over time. And that's because you're wearing off the yarn dye and getting more to the core of that yarn, which has not been dyed. And the last example is solution dyed. So solution dyed is manufacturing for typically filament yarns or staple yarns, but this is always man-made yarns where the color is added, or color or pigment is added before extrusion. So solution dyeing results in solid color all the way throughout the yarn, not just the exterior. And solution dyed yarns are good for outdoor applications because when you have the color throughout the full yarn, that will help prevent fading. think this is our last example of dyeing, and this example is for piece dyed or garment dyed. So this is you make the white yarn, or the example shown here is you make the white yarn, you then sew your t-shirt, you make the yarn, then you make the fabric, then you sew your t-shirt, and then once the t-shirt is shown, or the piece, or the garment, then that garment is dyed as one whole piece. So when a product is piece dyed, all of the dye receptive components in that element, like the care tag or the sewing thread, can potentially pick up the color of the dye bath. So you can see in this example here of men's t-shirts that even the care tag in each of the t-shirts has been dyed that color. This is an example of true garment dyeing or piece dyeing. And the last, so the next process after dyeing is typically finishing. So most fabrics require finishing, and finishing is any combination of processes or chemistry additions that give a fabric its final properties and improve its usability. It's pretty loose definition here, but fabric that has not been finished is referred to as gray fabric. Finishes that can affect appearance are brushing or napping, embossing or calendaring, moire, shearing, crushing, flocking, and there's more. But these are some examples of if you can heat set a fabric, but then you can also do things in finishing that affect the appearance of the fabric. There are also finishes that can affect the performance. For example, during finishing, you can add treatments for stain repellency, water repellency, wicking, wrinkle resistance, anti-static, antimicrobial, flame retardancy, and more. So this not only can you affect how a fabric looks in finishing, but you can affect how a fabric will perform. So the big takeaway that I want everyone to have from our Textiles 101 today is that the property of any fabric will be determined by the combined characteristics of its fiber, yarn, construction method, and then dyeing and finishing method. And that is it. Conclusion. Thank you.
All right, thank you so much, Alyssa. We do have a few questions that came in, and I will start with those. Which dyeing process is better, beam, jet, or pad?
It really just depends what you're trying to do. Beam dye can sometimes be more cost effective. You don't need as big as a manufacturing footprint. Maybe it uses less water. And then jet dyeing would be really if you wanted to impart softness to the fabric or bulk. I think in manufacturing textiles, there's really not a defined way of what's better than the other. I think it's more of a what are you trying to accomplish? If you have a specific end use, I'd be happy to kind of talk through that a little bit more.
Okay, great. The next one is, with all of the current conversation around bleach, cleanability of upholstery fabrics, is there one method of dyeing fiber yarn or solution on poly yarns or fabrics that wouldn't work for cleanability? Or is it more about the dyes used?
So cleanability of a fabric is It depends on what fiber type you have, and then the stain or thing you're trying to clean off of it that's on it. For example, a polyester fabric is oleophilic, or it loves oil. So if you have a polyester fabric with a grease stain on it, that will be more difficult to clean than if you have something that is water-based. I think there are finishes that can be added to fabric to help resist stains and prevent staining, but unless you have that water barrier, I don't think there's a dyeing method that can help resist the stains specifically. I think it's more maybe some finish that's put onto the fabric, or dependent on what is causing the need for the cleaning.
Okay, next question is how long does a treatment in finishing for, say, FR or antimicrobial last?
So it just depends on the durability of the chemistry used. Fire retardancy or antimicrobial can be added to the fabric in different ways. Typically, when something is added to the pellet before it's extruded, or if there's a property that's imparted to the yarn, it typically has greater durability than something applied topically. If you wanted to test the durability of properties such as fire retardancy or antimicrobial, a test you could do for that is a wash test. So there are labs that can, you do repeated washings at whatever number you would designate and test the fabric for the antimicrobial or fire retardancy property before or after washing. I think it's also something you can talk to your manufacturer about to learn how the antimicrobial or fire retardancy is applied to the fabric, and then just combined with how the fabric is being used would help understand how durable that finish would be.
Great, and we have one final question. What would you consider the main differences between industrial or load-bearing fabrics and consumer or wearable fabrics?
So in industrial fabrics, there's a very broad definition. So what's so exciting about IFAI and visiting the show is all of the fabrics have a functionality for industrial fabrics. There are apparel fabrics that are industrial. For example, if you think of like a fireman's suit or a spaceman's suit, there definitely are those sort of applications. I think what's different about just a regular consumer apparel versus industrial fabrics is the performance characteristics, basically. So when we're buying something for everyday use, we're not looking for a certain durability, for example, of like a glove or fire retardancy of a fireman's suit. I think those are really the main differences, that the industrial fabrics have very specific performance requirements.
I see we have a few more questions coming in, so we can dive into those quickly. How does the number of filaments affect the dyeability of yarn?
So I'm not sure that the number of filaments would really affect the dyeability of yarn. I think it's definitely possible to dye the yarn regardless of the number of filaments. Maybe it would require some extra time to make sure that the dye is imparted. Also, with filament yarns, it's possible to do solution dyed yarns. So that is when the pigment is added before. But I don't think there's an inherent problem in dyeing yarns with higher number of filament.
Okay. Are there other terms used for warp and weft?
Yes, there are. But those are the best ones, so only use those. Just kidding. I think woof is one that is out there for weft. That is pretty common. Sometimes the warp direction can be considered the machine direction, and weft can be considered the cross direction. That is more common in like a non-woven fabric where you don't have a warp or weft, or it's more difficult to identify because of the construction method.
Okay, and we will leave it with this final question. How can you measure the filtration properties of different fabrics?
So I think it would be working with a testing lab. First, you have to define what you're trying to look for filtration of. Is it particles? Is it a microbe? So you have to define what you're trying to filter. And then there are ASTM tests that exist for filtration. And I think if you work with a testing lab, they would be able to guide you into selecting a test that would help define fabrics filtration.
Excellent. Well, thank you so much, Alyssa, for all your excellent answers, and thank you everybody for all your great questions. Of course, if you have any additional questions, please feel free to contact Alyssa directly. We are just about to wrap up here. Everyone, just wanted to let you know that IFAI has a robust upcoming webinar schedule that we would love for you to take part in. Please check these out and register at our website, ifai.com/events. Thank you again, Alyssa, for a wonderful session today, and thank you all for attending, and have a wonderful rest of your day.